So next up is Paul from ADI. ADI is one of the platinum sponsors of the conference. So I'd like to hand it off to Robin, who is going to open.
Thanks a lot. So before we get started, just to try and set up the context of what Paul's been working on. For those people who don't know who Analog Devices is, we're a large semiconductor company. What we try and do is solve these real-world difficult problems that everybody has. So what you'll do is you'll find us in a lot of the USRPs, you'll find us in a lot of the EDIS products, and a lot of the wireless radios that you use and love every day. Inside those, the magic that happens inside, or from my opinion, the magic that happens is inside the chip. We deliver these solutions that others can't solve. We really try and stand for passion and success. One of the other things that we really try and do is focus on education. And so we actually work very closely with FIRST, support a lot of STEM initiatives, including FIRST and other things, have low-cost engineering tools for like freshmen in high school to understand electronics, the beginning pieces, parts kits. And one of the things that we've kind of come to the conclusion is, you know, there's a big difference between when you're starting out in high school, what you need as an instrument or a piece of hardware to play with versus what you need when you're a professional or a master's student or PhD or these kinds of things. And they kind of vary as they go along. So what we've been doing is we've been working on what we affectionately call our M2K. So this has a 100 megasample ADC input, 150 on the output side, 12-bit ADCs and DACs, plus minus basically 20 volts on power supplies. And so what we need for this is actually a great graphical user experience, a great GUI. And what Paul's going to talk about is how we've taken GNU Radio and implemented it into this GUI for this non-traditional SDR application to give people an instrument interface. Thanks.
Try now.
Hello. Perfect. Thanks. Yeah, so I'm going to talk about the project I've been working on at Analog Devices for the last year. So before talking about that project, I'm going to talk about the I/O oscilloscope. So the I/O oscilloscope was the program we've been using for the last few years. It's basically a software oscilloscope written in C using GTK. Developed at Analog Devices. And before 2014, it used to talk directly to the I/O subsystem of the Linux kernel, so through device nodes and sysfs files. Shortly, I/O stands for Industrial Input-Output. It's a framework of the Linux kernel that came out in 2009, developed by Johanton Cameron. In 2012, it moved out of staging to become really part of the Linux kernel. And it's basically the area in the Linux kernel where you will find all the input-output devices that are not human interfaces. So for instance, sensors, accelerometers, thermometers, also for high-speed transceivers. In 2014, libio was born, so you probably already heard about it. I did a talk about it last year. libio basically is a software library that allows you to develop application that makes use of I/O devices. It has a simple and stable API. And it abstracts away all the complexity of the I/O framework. So in 2014-15, libio got a network backend as well, and the corresponding server called IIOD. The interesting things about this is it enabled the possibility to run the I/O oscilloscope remotely. So have just a small server running on the development board that will stream the data on the Ethernet link, and then run on your Linux laptop or PC the I/O oscilloscope through the Ethernet. And that really improved things. It was much easier to debug, and the performance was actually much better because we were not doing any processing on the target board. All the processing was done on the PC. And last but not least, it finally opened the way to run the I/O oscilloscope on Windows. Yeah, today the I/O oscilloscope is we're trying to improve it and to get over it. There have been some developments made, notably in the LibIO. For instance, it has a USB backend to be able to talk to USB devices. But the I/O oscilloscope is already too old and not structured correctly to support those USB devices. And that's not the only problem that we have with the I/O oscilloscope. So it uses GTK, which looks okay on Linux, but GTK is really not well supported on Windows, not very tested, not very stable. It's actually quite buggy if you start to use threads and everything. And it's not very sameable. So it looks good on Windows. It looks really bad on, it looks good on Linux, looks really bad on Windows. Then the compilation for Windows. So we did set up automatic builds of the I/O oscilloscope and all the dependencies, glib, GDK, etc., on the build machine, and that was not a really an easy task. So that's something we can do, but that's not something that our clients can do if they, for instance, want to modify the I/O oscilloscope and want to rebuild it for Windows. Then we can't just tell them, yeah, you have to rebuild all the dependencies. Yeah, and last point, I write C is not easily portable, and POSIX is broken. So I consider myself good enough in C to be able to say that. I learned recently, so there is one function I used to use all the time called SDR copy, like basically string copy from a string to a buffer. So it takes 3 arguments, buffer pointer, a string pointer, and size argument, which is the size of the destination buffer. What it does is if the size is bigger than the string, then we just copy the string and then fill up with zeros. So if your buffer is 16K, and your string is just 100 characters, it will copy 100 characters, then basically fill with 16K zeros. And that's already bad. It gets worse if the size is actually smaller than the string, because then it will copy the beginning of the string and won't copy the \0 at the end, the string terminator. So basically, when you try to print the string, you will end up printing random memory at the end. So we've been having quite some problems with C as well. For instance, if we want to use threads, we have to use pthreads on Linux, but we can't use pthreads on Windows, etc. Visual Studio barely supports C99. And the idea was to switch to C++. That is much better supported on Windows when developing the new project. New project called Scopy. So basically, Scopy is a software oscilloscope and signal analysis toolset that was created more or less 1 year ago. It's written in C++11, uses Qt5. It's open source, licensed under the GPL3. The sources are on GitHub. The objective was to develop a modern, touch-friendly, cross-platform application that has the features of the I/O oscilloscope and more. So just for reference, here are a couple of screenshots of the current application. So that's the oscilloscope view where we have just 2 sine waves on 2 different channels with the trigger vertical and horizontal bars. That's the voltmeter view. The signal generator view. So I don't know if you see the blue one correctly. We have a blue sine wave and a small square signal on the top that we generate. Scopy uses libio as well. It uses the USB backend of libio. It can also use the network, over the network. And the interesting point about the software is it actually uses GNU Radio and the GRIO blocks. So the full stack, basically, we have the Linux kernel that handles through the IO drivers, all the devices. The libio will talk to the Linux drivers, yes. The IOD will share the libio context on the network and stream all the data. On the other side, you have again libio that will use libUSB to talk on the other end of the USB cable. libio will be used by GNU Radio and GRIO, and Scopy will use GNU Radio. So what was the idea at the very beginning about using GNU Radio? Well, we figured out you can actually, in GNU Radio Companion, just drag and drop one source block and one sync block and link the two. And you already have like some very basic oscilloscope. What we just needed to do was to add more controls, improve the visuals, make it pretty. So the idea of having GNU Radio at the core was since the beginning. Besides, GNU Radio provides lots of DSP blocks that we could use if we want to. And it already had Qt-based plots, which was great because we wanted to use Qt. So we actually use GNU Radio as a piping system. The major problem we had with this was that we have only one source of data, which is the USB device, and multiple clients, which are the tools. And we want to be able to enable, disable the tools independently of each other. So if, for instance, we have the voltmeter running and the oscilloscope plot running, we don't want that by stopping the voltmeter, the oscilloscope plot stops as well. So the solution we found was to use the copy block, which has an enabled parameter that we can toggle at runtime. So the enable parameter, what it does is if it's set to enable, then the data will be copied from the input to the output. And if it's set to disable, then the data will be just dropped without blocking. So typically when we start a client, let's say I just open the oscilloscope view, what we will do inside the application is add a new copy block and connect it to the plot or the whatever the client uses. And that copy block will allow you to enable, disable that particular client. Yeah, if we add another one, then we can just enable, disable them separately of each other. Quickly, a small word about the trigger mechanism. So that's something we thought would be much harder to do. So at the libio level, we have buffers, and we know exactly the position of the trigger point in the buffer. The problem is once we pipe that into GNU Radio, all that information about buffer boundaries are lost. That was before we learned about tags. And what we do actually is just add a start of buffer tag every time we refill the libio buffer, and just synchronize the plot on that tag so that the top left sample we see on the plot is the beginning of the buffer, and then the trigger point is always where it should be. The GNU Radio, the fact that we use GNU Radio and Scopy really starts to be interesting when we talk about masked channels. So when I talk about masked channels, I talk about the virtual channel whose data is the result of a mathematical function applied to one or more hardware channels. So for instance, there, the green line is actually the multiplication of the result of the multiplication of the two hardware channels. The way the IO oscilloscope did handle that, what it was doing was basically you type in a function, then it will generate a C file It will call the host GCC to compile that file into an object file, and then use the system called dlopen to load that file, link it dynamically to the program, and then call the function that is inside. So it did work under Linux, but then you had a hard dependency on having GCC running on your host system. Like, it didn't work if you have Clang, for instance, and obviously it did not work on OS X, or it did not work on Windows. The way we do it in Scopy is very different. So we have a mass or function block that is provided in GRIO. That block has one float output and one or more float inputs, and it has a function parameter. What will happen is when you type a specific function, it will be parsed using the GNU Bison Flex tools. And you will have a flow graph of blocks generated, and that flow graph will represent the function. So for instance, for that function that is on top, fx equals sinus x times sinus x minus p squared, that will be the flow graph that will be generated. So we have a source here, path source, which is basically our x. We apply the sinus function on it. We also subscribe pi, apply the sinus on it, apply the square, and then multiply the two, and we get the result. And that's something we use for the function generator as well. So in Scopy, we have a function generator, a sine wave generator, and one of its functionalities is the ability to generate a sine wave from a mathematical function. So how do we do this? Is actually we just use the mass block, and the input data of the mass block is a periodic sawtooth that oscillates between minus pi and plus pi at a certain frequency. So just for reference, this is like the output if you connect directly the function generator block to a Qt time sync using the function that I showed before. So on the things that went wrong, so I guess most of the people here, when they work with Norio, they make one flow graph, and the flow graph is static, or it won't like change that much. But every time we need to enable, disable one tool, we do connect new blocks, we disconnect all the blocks. So we do a lot of graph reconfiguration. The problem with that is, so unless we missed something big, we didn't find a way to disconnect a branch from the GNU Radio flow graph. Basically say all the blocks connected directly or indirectly to this block, disconnect them. So that's something we had to do, like in Scopy, memorize all the blocks and memorize all the connections, basically recreating the connections between the blocks in Scopy, like the graph. But that's like pretty much all about the things that went wrong. I mean, I'm surprised myself that Norio worked really well in that context. So we did a couple of developments that can or will be useful to the Norio community. First of all, so Scopy is cross-platform. It runs on Linux, on Windows right now. And so that means we had to update the GNU Radio port to Windows, test it. That's something we participated in. Also port the Qt GUI blocks to Qt5. And finally, well, the function generator blocks that I think are very useful, can be reused. Final thoughts. So GNU Radio has been very useful for us, and it can be used, and I say it can be abused because it's actually not a tool made it's a tool made for SDR applications, and we use it in software oscilloscope that has nothing to do with SDR, but it actually did work very well. Yeah, so thank you. If you have any questions, I can answer them right now.
All right, are there any questions for Paul? I have one right here.
How does the function generator block know what functions are available?
Yeah. So that's a good question. That's basically all the functions you have available in the transcendental block right now. So the transcendental block supports sin, asyn, cos, acos, square root, probably a log 10, and it's not like a wide panel of functions, and it could totally be improved. Actually, the mass block generates a flow graph and could totally generate all the blocks according to function names. So if you have ABS block to calculate the absolute value, then you could say, hey, if you find that ABS string in the function, then you generate that block, and that would totally work.
Are there any questions for Paul? No? Okay, I actually have a question for you. So I noticed that the license is GPL v3, and obviously you're linking against GNU Radio. So my question would have been, had you chosen not to use GNU Radio for this project, do you think you might have made a different license decision?
Yeah, so we are using actually not only GNU Radio, but we are using libio as well, which is actually it's LGPL, so we could have done that. Well, that's a good question, but I would say that since the very beginning, it was clear that it was going to be an open source software. Since I've been at Analog Devices, I've been working on open source software, and that was the plan was not to change that.
Do we have any other questions for Paul? No? Okay, let's thank our speaker. Thank you very much, Paul. All right, so there will be another talk from Analog Devices later in the conference. And before we break, I want to go over just a few things. So as we went over at the start of the conference, first of all, this year, all of our, every talk is being recorded professionally by our professional videographer team here in the back. So unlike last year where poor Jose was trying to manage a whole bunch of little home theater cameras and then editing themselves and getting them on YouTube, we're doing this for real this time. So all the talk recordings will be live online on YouTube as soon as we get those at the end of the conference. The other major item this year is we have published technical proceedings. So these are now live. We have 10 papers published this year. And if you go to pubs.gnuradio.org, you can see all the papers have been published, and they're also on archive. So we now have, I think we're just a touch ahead of schedule. For some reason I can't see the clock up there. So we're going to reconvene at 3 o'clock. And there are afternoon snacks off to the side. And yeah, I'll see you in half an hour.